Hello, ladies and gentlemen. It'd be my great pleasure to introduce to you our speaker for this session. His name is Jake Holland. He's a software, or historically, his background is software engineering. Now, as a principal architect with Akamai, he's going to talk to us about IP multicast, the next steps to make it real. Jake, if you would, take it away.
Great, thanks, John. Yeah, so I'm going to be talking about IP multicast. I've been working on it at IETF lately. This is some of the work that we've done, and we're going to be building this out and trying to make it actually, deployable and in fact deployed. And that's what I'm doing here today. We want to make sure that this actually works when it's rolled out, and in order to do that, we think we need to, talk to some network operators and make sure it's going to meet their needs. Make sure we understand if there's parts that are blockers in what we have not solved yet, and that we address them if that happens. Our plan is to get this rolled out in a browser API as sort of the main receiver path. And that's going to open up a whole lot of content for us to use, and probably other people as well. That is underway now. We've just filed our intent to prototype in Chromium, and that's going to take a little while. But this is the sort of early engagement phase where we make sure that as we get the browser implementation rolling, that it actually is going to work in the network as well. And we think we've defined an open standards-based approach that should be repeatable and not any provider-specific implementation. So we think that this is going to work okay, as best we can tell. But obviously, this is early days, and we want to make sure that we get the good engagement and feedback that can really make this successful. And that's what I'm doing here. So I'm looking for review on our specs, looking for feedback, and to just sort of get this idea out there and get people thinking about it and looking into the future to make it happen. And hopefully, I would love to find a few brave souls, visionary, forward thinkers who are willing to do some trials with us this year and make sure we can really test these things out and make sure that they would actually work at least in your networks, and that we can do what we think we can do. So I'm going to go through. I'm going to spend a decent amount of time on motivations here, like what we're trying to accomplish and why we're trying to accomplish it, and why we're focusing on multicast for this effort. I'm going to give a super fast run through of what we're proposing, and why we think it's something that can solve the challenges that we know of with multicast deployments between domains, and go over like what we're going to do in the trials and what we're looking for in these trial partners. We're also offering to share some data personalized to your AS about what the traffic mix that we send looks like, so that you can make an informed decision about whether the traffic that we're providing can provide a good business reason to get this working on the kind of timeline that we're looking at for rolling out the browser capabilities, and perhaps other receivers too. But the browser, we think, is going to be a real game changer in this, and make it viable on the receiver side. And so we're digging in on that quite hard. So I'll jump into the why multicast first here. Part of it you may have seen. This is a couple of messages from the NANOG list in the last few months, talking about just some of our relatively high traffic days. These can be disruptive for lots of people. We understand that, and it's it happens. And I'll go through a little bit of what's going on when that happens, and talk about why multicast really we think can help here. When you just do the math, it turns out to get pretty clear. So I picked 167 terabits per second here because that's our currently published record for the amount of traffic delivered to end user at peak. So that's that goes up every year. We're always rolling out new capacity like everybody else, right? But when you consider things like there are popular games today that have 100 million users, and some of those popular games, sometimes they ship an update that is like 65 gigabytes. And when you just multiply those bits together and you divide by by our record traffic, and you say, well, what if we served that traffic at our record rate as best we could and did nothing else with our platform, which, by the way, that would be an upper bound on what you could have expected to see in the past. When you just do that division, it turns out to take 3.5 days to deliver all that. And this is a big mismatch, like an order of magnitude at least over what a user would expect, because like if they're looking at a 50 megabit network that they're paying for and they're thinking it's a 65 gig download, then they're looking for a 3-hour download, right? So this is the mismatch between supply and demand that we're trying to address with our multicast capabilities. And it's not just like the game downloads. I mean, the OS updates have the same kind of trouble. That is the same exact bits has to get to like everybody who has that kind of computer, right? And it's really inefficient to do this with unicast, and it really shows when you do that math. And likewise, the kind of traditional use case for multicast. This is another one that we think we can address. We have a product that does this today, but I'm not here to talk about that. It's but that would be the sort of early version of the trial. The traffic we'll be running is the live video, but we do want to get to that download because we think it's really important. But when you look at the same story on live video, like okay, we sometimes ship 167 terabits per second at our peak load. What can that accomplish if we're looking at like 4K traffic, right? Well, 4K typical bitrate is about 40 megabits per second. That's like YouTube guidelines. And when you just multiply that out or divide that out, then you end up with like 4.2 million viewers is how much 4K traffic we can serve. Like how much is that? Well, it's not actually that much. It's like the 117th most popular TV show from 2018. I mean, the Super Bowl is like 100 million people, right? Even if we only have a small portion of that traffic, if people are trying to watch it in 4K, there's this giant mismatch between, even what a major content provider or content delivery system and it can do and what the demand is, especially as more and more devices go online. And it only gets worse from there, right? I mean, more and more 4K TVs are getting rolled out, and there's now 8K TVs rolling out, and there's talk of doing VR. There's like some prototype stuff that's essentially 12K at 400 megabits per stream. You look at the Cisco reports, and they're predicting have been for years 20% year-over-year growth for the demand in per household traffic, and a whole lot of this is just addressable by dealing with multicast. So this is what we're looking at for what we think we can address. This is traffic from January 2019, and this is kind of the traffic mix that we see. It's pretty typical. This varies a little bit, but we think that the software traffic, a whole lot of it is addressable. And we think the live video is almost entirely addressable for anything that's widely shared, even though it's a relatively small portion of the overall traffic. It works very efficiently. That and the software does. But we also think we can address a lot of the we call this the mixed live and video on demand, and this is the video on demand that's actually being concurrently consumed. Right, so even though the multicast can't easily necessarily address on-demand video that's truly on demand, the video on demand that's like when the new show comes out and people happen to demand it within the same 15 minutes for like 80 or 90% of the downloads, well, that actually is pretty addressable, and that's something that you can do just by like offsetting when you start your, have a different carousel. So depending like which 5-minute or 1-minute section they happen to start watching in, they can get most of that traffic with multicast if we just set it up right. Like it's not as efficient as live video, but it's far, far more efficient than unicast. So, our overall targets, what we think would make this worthwhile for us and what we're aiming to be able to achieve with any networks that can do the delivery is to reduce our peak load by 50% and to reduce our day-to-day bandwidth load by 20% overall traffic. So that's, based on sort of what we deliver today and what we think we can change into multicast in the future going forward as this becomes more widely available, under the assumption we're successful. That's where we're aiming to get to. So just to give that kind of background. So now I'll talk a little bit about what we're actually trying to accomplish and why we think it's going to work the way why we think it'll be doable, or at least we hope it'll be doable. And that's what we're looking for feedback here from you guys on. So this is a network diagram from our architecture deck that we go through with people who are interested in talking about this further with us. What's happening here is the multicast traffic gets ingested as a unicast tunnel. So this uses AMT, which is a proposed standard RFC. It's 7450, and it gets unwrapped as generic UDP traffic inside the multicast capable portion of your network. So you can run these ingest points, in a place that makes sense for your network. It can be right near, your pairing points, or it can be a little further down where there's actually like a bottleneck that you'd like to get traffic shared on. And that can be kind of, different networks have a different places that make sense for where to deploy this. And that, any location that makes sense for you should work essentially the same. This, like I said, this is supposed to be open standards, not provider specific, and just make the whole thing work automatically. And what happens is that we're planning, at least for the traffic we're delivering, for the foreseeable future. All the traffic is going to be available over unicast and using unicast whenever multicast is not available, because we think we're going to have to operate in networks where multicast is not available for some time to come. So anywhere that unicast is being used, then the receivers, when we notice that the traffic is popular enough, then we start sending headers to the receivers to tell them, hey, by the way, there's some multicast available here too. And the receivers will just go ahead and try to do that, do the join. Our architecture relies on source-specific multicast, so it's going to be an SSM join using GMPv3 or MLDV2 if you're using IP6. And after doing that SSM join from inside devices in the consumer's home, like browsers or the set-top TV boxes, or the smart TVs, then that join propagates through the network. You get to decide, are you going to allow this or not? And we publish a bunch of metadata. So this is part of the specs that we're building out now. We publish some metadata to make information available to you about what is going to be inside that stream that you're going to be deciding whether to allow through your network or not. How much bandwidth is it going to be in particular? And these are specs that are under development and can be extended at this point. So this is a good time to articulate what has to be there for this to work for you, right? But the metadata that exposes how much bandwidth is going to be used by this stream can be used as part of the decision for whether to allow the stream in, to make sure you're not getting oversubscribed. You can couple that with like how many users are trying to join it right now, and make an intelligent decision for your network as to whether this multicast traffic should be propagated through this network. Other providers can use the same kinds of techniques. We're focusing on the traffic that we want to run, but the architecture is intended to support whoever wants to set up the same kinds of metadata publishing system that we spec'd out in this work that we're doing. So as the signal propagates back to the ingest point, wherever it's located in your network, the ingest can automatically discover the right place to connect a unicast tunnel and then pull that multicast traffic into the network. And then from there, it's forwarded as native multicast traffic within the network. As long as the users start getting that traffic, then they'll stop using the unicast to perform their download and will favor the multicast instead. All right, so that's the basic outline of the idea. And this can be used for many different use cases, not only the download and the live video, but also future use cases such as VR that may not yet be fleshed out, or we're not sure if other use cases will come up. I think once this is available, assuming it becomes available, then people will find all kinds of good reasons to use it. But we have certainly a few things that we want to do with it that we know of up front. So thanks to John for pointing out this is a really useful information for network operators. This is the network changes that we think need to happen to make this possible. So at the ingest points, you need to deploy an AMT gateway and the discovery that lets you automatically discover where the right AMT connection you should open up, where that AMT connects to open up the connection to access the traffic that you're trying to join. At the choke points in your network, these are some of the drafts that are there. This is how the metadata gets published and what is inside the metadata to expose the bit rate that the traffic will be consuming. And that would plug into whatever kind of bandwidth provisioning safety mechanisms you've got inside your network. And this is the part that would be fleshed out during the trials that we'd like to do. That's a big part of it. Obviously, within the network, you're going to have to, get those packets delivered to the end users, and that would be, however you do your delivery. We recommend. We have some recommendations in our architecture deck, and we can walk through that if you're interested in following up further. And then the other big piece is the CPE, and this might be the heaviest lift depending kind of where you are on this kind of a system. Like in Europe right now, when I went and bought some of the off-the-shelf home Wi-Fi routers, and by CPE here I mostly mean the home Wi-Fi routers, they had both of these pieces already there. Like the IGMP, if you do a join from inside that Wi-Fi router, that router will just propagate it right on through, and you can handle it as the network that's upstream of that, and propagate the join or not according to what your network logic is. And then also the multicast to unicast conversion is another piece of this that's important for the Wi-Fi connected devices, and there's not a standard about this, but it's interestingly part of a default part of the Linux kernel and available by default in at least the open WRT based systems, and we think a bunch of the other ones, although it's hard to be exactly sure. But the point is that and what it does is it makes it so that at the Wi-Fi layer, it's going to be sending unicast packets to the end devices because of the troubles with Wi-Fi multicasting. So the point of highlighting the CPE parts is that if that is the heavy lift for your network, then it's something you might want to start looking into now. Like the pieces are available, but you may need to apply the appropriate sort of incentives to the vendors as you might be able to make sure that that feature is there for the routers that you're approving for going forward in the future for use in your network, and maybe the ones that you're providing to people who do the upgrades if you're managing their upgrades. So that might be a disqualifier for some networks, and I want to make sure to or it might make it excessively hard for some networks, and we know that, and that's why we want to point it out to you and make sure we're not wasting your time. But if you think you can address this, then we think that there might be some value in doing so as you go forward. There's also some changes we'll have to put up to make this all work, and we're planning to do all this. The big one is getting the SDK delivered, and I'll go into a little bit more of our plans there. Obviously, the browser is a big part of that, but something on the receive side needs to be able to receive that traffic and turn it into the thing that's actually being delivered, whether that's a software download or playing the video feed, and they have to understand the contents of that UDP traffic. But part of the point of this kind of architecture is to make that not be your problem as the network, right? As compared to like the IPTV systems that you might see used with multicast today. And we need to publish the information that you guys would be using to make sure that the tunnels can get set up, that you've got access to the metadata that you need to make intelligent decisions about whether the traffic should be forwarded in your network. But we think that that's all we know of so far that needs to happen for this to actually work out okay. And we think we can handle all this. This is quite tractable from our side. And it's worth highlighting some things that don't need changing here, right? We don't need any like special peering or SLAs about this. The idea is to do this more like the way that website traffic is delivered, right? Your users have asked for something, and the thing that they've asked for is freely available on the internet, and according to whatever they've signed up for. And by just passing that through and getting the packets to them, if you can hook up this multicast capable scenario, then you can really save a lot of the traffic that has to be delivered, and it can be a really valuable win-win for everybody, and make your users happier, make our users happier. And this is all provider neutral, so that if it meets with success, then other people can start using it too, and more offload can happen that way. All the tunnels get auto-established and worked out, which I'll point you to the specs on how that works, and I can walk you through it if you choose to dig in on this further. And the other thing is that there's no encoding that's happening within the network. So by contrast with the IPTV, multicast-based TV systems or something, where what you do is you ingest video, and then you take that video and you turn it in your own vendor's way into like the packets that get forwarded on the network, and you forward those packets down through the network, and now you have to have a thing that you're maintaining that's sitting somewhere that receives those packets and turns it into actually video, right? And that has to be either on your set-top box, but like, do you want to put it on all the smart TVs, and do you want to put it on your phones? Like, maybe you do, and that's fine. But the same kind of architecture can be used to deliver that as to deliver some of these other kinds of use cases that we'd like to achieve, and other video that's not necessarily sourced directly from the content owner into the network, like with the triple play solutions. And it allows you to treat all the different use cases as the same kind of thing, where it's just UDP traffic that you don't have to worry about exactly what's inside there. You just, like, as long as it gets shipped to the right place, then that's somebody else's problem as to whether it can be decoded properly. It's UDP multicast, just delivered all the way through. The receiver join logic in this scenario is that like I said, we'll be monitoring as a CDN for the traffic that we're delivering, whether this will be whether this is sort of sufficiently popular to justify creating a multicast source for it. And if it is, then we will start off our source. We'll populate all the things that need to be there to make the connection successful according to this delivery architecture. And then the headers will start coming to the receiver to tell it that there's multicast traffic that you can use to get this instead. It'll join those flows, and if it does start getting multicast traffic after that, then it will stop using the unicast. This requires putting out an SDK of some sort, something on the receive side at least. So for the trials that we're talking about, we would be, and perhaps some especially early side deployments, We would be doing this with an SDK that would be built into the content owner's app, or perhaps an app distributed by us if that turns out to be the better way to do it. And it would be interoperable with the traffic that we would be generating. We think we need to do this because there's like 8 different protocols that people use for delivering the traffic. Broadpeak has a proprietary one. We have a proprietary one. There's a few other competitors. I think Ramp was mentioned. There's the MPEG encoded TS and a few different versions of Flute and Norm that are used by some DVB systems. So there's several different systems that are in active use today, and we don't think there's enough cohesion to just pick one and run with it. So we're trying to make this, we're plugging it at the generic UDP level. And what that means is that there has to be something that receives that traffic and interprets it properly. And that's where the SDK comes in. And the browser-based API is the next step of that, where the browser would if we're successful in that rollout, would gain a W3C standardized API that can receive authenticated multicast payloads that arrive by native multicast to the browser, and deliver that into a JavaScript-based program or a WebAssembly-based program, and then the WebAssembly can be delivered on an ordinary web page. So that's the way we're trying to roll that out, and we think that eventually you might be able to get some efficiency gains by standardizing the actual transports that are used and putting that into the deeper into the browser and integrating at a lower level than at the WebAssembly. We're not sure if it'll be necessary or not, but that's kind of the longer term way this might fall out as we get some cohesion in the various standards. But we also think that it can work for quite a long time with just doing WebAssembly and handling whatever kind of traffic both the sender and the receiver can agree on. The way the ingest works is spelled out in these 2 specs. The AMT establishes a unicast UDP-based multicast UDP-based tunnel that contains native multicast traffic. So you receive this join as you're propagating the join backwards in the network along the reverse path, and the multicast routing table would direct that into the ingest router if it's traffic from outside your network. So that's the part that you would set up. And then that ingest router would take care, or the set of ingest routers, perhaps, if you want to shard it according to the different sources. And what that ingest router would do is discover the right tunnel to connect to, open that tunnel, send the join through the tunnel, and then it starts receiving this unicast encapsulated traffic that is native multicast, and then it forwards it from there within the network as native multicast UDP traffic. And Dryad is a piece of that's our sort of first step along this architecture path. That was recently finalized as an RFC and is published now. And what this buys you is this is the part that means that you don't have any explicit peering, but you can do a provider neutral ingest of arbitrary UDP traffic here. And it also means that the location, both for the AMT relay and for the AMT gateway that does the ingest, can be flexible according to where makes sense within your network and where makes sense for the provider of the traffic to run those tunnels. Now, maybe this all sounds kind of pie in the sky. And maybe it is, but we do recognize that there are challenges in making sure you don't get over provisioned, and we've tried, and that the traffic delivery meets all the right safety standards. And this is what we've tried to outline in these documents so far. And this is where we're really looking for feedback as to whether this is enough, whether this works, whether there's other pieces that we really need to address so that we can get on that and make sure that this rolls out successfully. I mean, there's no point in writing these specs if it doesn't get deployed. So, and we will walk away if really nobody is interested at all in this. But we think that this can really provide a major win for everybody who engages with it. So we're trying to make it happen. So these are the specs. The dorm spec is how the metadata is discovered. It's adopted by MBOND and it's a work in progress now, targeted to become a proposed standard RFC. When we are done and ready to nail it down. And what this does is this is the generic way to discover the metadata. This actually defines a Yang model that runs in a REST-conf server, and that's the API that we're using to publish a standardized set of metadata and lay out exactly what's going to be inside there. And then CBAC is circuit breaker assisted congestion control. And what that does is define the circuit breaker behavior to do if you realize that you've been oversubscribed, that your network has become oversubscribed or is prospectively oversubscribed, to cut it off and make sure that that the traffic you're forwarding fits within the amount of bandwidth provisioning that you want to dedicate to multicast traffic. So that's an extension to the metadata defined in dorms. So it adds into that into the tree that dorms defines, the Yang tree that dorms defines. It adds in the bandwidth information and perhaps a few other things such as MSS to make sure your MTU is okay. Things like this. There's also we've worked on transport authentication. So this provides per packet authentication of the UDP data that we're sending. And this is authenticating the UDP payloads. We think this is a necessary component in the browser. So we're doing it for the browser usage regardless. You can also use it to detect loss. So even though you don't know the protocol of what's being transported inside UDP, you can still determine whether there was lost, whether there were lost packets by plugging into this specification. And you can determine that the packets that you're receiving to forward through your network are exactly the packets that were being sent by the sender. So in the network, this is optional. The browser is going to be doing it anyway. But if you wanted to add this kind of a firewall-y behavior to try and protect your users, then this is an option to do as well. And then what are we looking for? And who do we think can be involved? As I said, this is like trying to be standards-based and repeatable. It's a open standards approach, so anyone who can make it work can get involved in this. And we do expect to see, if it's successful, competitors of ours join in and deliver some of their traffic in this way too. If you choose not to do it, well, that's fine. If traffic starts getting cheaper, that might be something to consider, because some people that do pick it up might be able to get some gains out of it and make it easier to deliver this traffic. So that's kind of where we see this going, if we can get any traction anywhere. And so we think it really does represent a good opportunity to get into this and start doing stuff. And you also might see content owners directly running their own sources for some of this kind of traffic. We think, we provide a good service, but we might lose some business to the content owners that are kind of technically savvy enough to bring this up themselves, because it does reduce the amount of load. We do think we've got plenty to do with our network, so we're not, knock wood, hopefully worried about going out of business over this. But really we have more traffic to deliver than is sustainable to keep doing as unicast, honestly. So that's kind of why we're trying to get this to work. So during trials and as we move forward with this, we've still got a lot of work to do to make this a reality. We've got an open source system here. You can pull it up and play with it, that has a basic implementation of the AMT ingest router with the Dryad lookup from RFCs 7450 and 8777. And then some further development would be needed on the dorms and CBAC approach to make sure that this can actually integrate with any reasonable bandwidth controllers that are out there. And if we need to iterate on that, then we're totally willing to iterate on that. This is part of why we're trying to engage here and make sure we get this right, so it's actually deployable. And then the browser API, of course, is in progress. We've issued our intent to implement, or our intent to prototype rather, and that's going to be a process, and it's going to take a little while. And it's going to rely on forward progress on the specifications that it's built on, which are these same specs that are under development in ITF. But that's something that's coming down the pipe, and we hope to be done with that within, let's say 2 or 3 years, and to start having, like, once that rolls out, then all of a sudden there will be a bunch of traffic available that for networks that can deliver it, it'll use multicast by preference for as much traffic as we can start putting on there. In terms of the trial that we want to do for this year, for ourselves and our partners, we want to walk out of that thing knowing what the actual cost is to get this fleshed out and done in an actual deployable setup. So we're going to, dummy things up and hackathon it to make sure that the proof of concepts work, and make sure that it kind of does what it needs to, discover and fill any of the holes that we find along the way, and make sure that it, when it's all done, it's actually going to be there, and get the information that we need to commit to a multi-million-dollar investment to to actually do the entire job of the engineering work that needs to happen. And if it means we need to update the standards and even develop new ones, we are willing to do that. It's that important to us. So the question for you then on would you want to participate in this trial, like, especially if you've already got any kind of multicast IPTV system, we think we can probably work on the same infrastructure with some work, especially if it's already going over the in-home network to Wi-Fi devices. We think that CPE part is, for some networks, quite likely to be the heaviest lift. So anybody who's already done that is like practically finished, and all you need to do is the ingest, we think. And we'd love to work with you and make this super easy. And what we think you get is, like, if you can actually stop having quite so much unicast bandwidth growing at quite such a rate, then maybe you'll be able to delay a bandwidth upgrade that you would otherwise need to do. And we're very much looking for feedback at this point in the process and trying to get the standards really fleshed out. So here's our contact information. That's me and my colleague, the business director on we call it the Disrupt project. We think it's a disruptive technology. And what we want to do is just start with a 1-hour walkthrough of the architecture, give you all the pieces so you can review it at your leisure, and give you answer any questions you might have, really dig into the nitty-gritty and the details and see if this makes sense for you to do, and give you the information I mentioned before about the AS specific traffic mix that you see, and how much of what we're doing today would be offloadable if this kind of an architecture were available. So you can make an informed decision about whether this makes sense for you. We don't want to waste your time. We don't want you to waste our time. If you're not getting a lot of traffic, then we don't really care if you deploy this or not, right? But if you are getting a lot of traffic, then we kind of do, and we'd love to have this work. So, and after that, we would just follow up as needed. So that's kind of what we'd like to achieve, and I hope to hear back from you, and I'll take any questions you got now. Thanks.
Jake, thank you very much. That was very, very interesting. And yes, I did watch the preview of it. So great stuff. Multicast is on its way again, I hope. We do have some questions. First question we have comes from Kevin Perry. What protections could we put in place to prevent this from getting used for DDoS attacks?
So the CBAC spec, if you check that out, there was a link to that from the early in the slide deck. That is circuit breaker assisted congestion control, and it's intended to address that sort of class of of issues. In general, the idea is that you've got some network protections to prevent you from getting oversubscribed. This requires some amount of implementation and integration with your with whatever you would use for bandwidth provisioning to assign multicast bandwidth space. And this is a key part of what we'd like to develop during the trials we'd like to run this year, and hopefully we'll get like good vendor support going forward. We think that that's a critical piece of getting this whole thing to work, and we're in general, the idea is that it prevents you from oversubscribing, and if you can get the there's an experimental PIM extension in, I think it's RC 6807. It's referenced in the CBAC draft that can provide a population count. So and there's a formula there for how it's recommended to prioritize the traffic if you need to do that.
Very good, thank you. Our next question comes from John Christoph, and this is one that I was thinking of myself. Support for interdomain IP multicast from source to end host sync strikes fear and loathing for some of us who have sustained battle scars. Is it possible to multicast to local caches and let clients unicast locally from there to reduce the deployment burdens and limit security concerns of receiver-directed state complexities? That's a mouthful.
Yeah, so I'm sympathetic. In some sense, I mean, possible is a funny term, right? Yeah, sure, it's sort of possible. And I'm not opposed to getting that in also. The architecture, or instead even, the architecture that we're putting forward here asks for connectivity to the end hosts and then provides protections, like I just mentioned with CBAC, to try to make it not the kind of thing that would inspire fear and loathing. Hopefully, we're providing the metadata and giving you the tools to ensure that there's safety that doesn't cause the kinds of problems that you may have experienced before. If it doesn't work, I mean, if we can't get any traction on this, then we are prepared to sort of fail over to that, but it has some different kinds of complications, and some of the advantages we think would be missing from a solution based on that, because now you're going to have to maintain this cache. You're going to have end users that can, reach that directly, and you're going to have to like have some decoder that's deployed on these gateways that has to interoperate with the sending side. So there's a different set of complications that comes into play. And it also has to be in homes if you're going to save the bandwidth space across the access network, which is its own sort of complexity introducing problem. So we've looked at that a bit, and we've come down tentatively on the side that we would like to see this deployed to end user devices, and we're trying to kickstart that by getting it into browsers, as I talked about, but and other apps that can do the native receive. But so that's our first choice, and we're sticking with it for now. But if we do fail there, then look for me to introduce a solution like that, because we got to solve the scale problem somehow.
Cool. I think we have time for one last quick question, and this is from Patrick Gilmore. Not sure where he's working. It doesn't say up here. How does the CDN bill for this?
So we're looking at this, at least for the near and probably foreseeable future, as a evolution of our current billing. So we are offering a service to deliver traffic, and in the limit, it might make no change at all, but we think that this would enable us to offer a discount on traffic that is successfully delivered over multicast, so that it can be, obviously if it reduces our costs, then we would love to pass that on to our customers in some form.
Very good, thank you. Well, that's all we have time for, unfortunately. Excellent talk, appreciate it. Two things coming out at the end. The Women in Technology lunch starts in about 30 seconds. Go to your agenda and click on the link. There's plenty of space. And there will be a poll this afternoon asking what people want to do for breakouts in BOF, which is a new feature for virtual NANOG. Thank you very much. Have a good day.
All right. Thank you. Bye.